Welcome. In the previous video, we understood that electric field and magnetic field are hand in hand while coming to the discussion of waves. Thereby, we call it as electromagnetic waves, and we can directly make use of Maxwell's equations, those equations which give us interdependency of magnetic field and electric field. Coming to today's point of discussion, that is uniform plane wave equation. Basically, if the electric field and magnetic field is lying in same plane and these fields are responsible for any kind of wave, then such a wave is known as plane wave. To be more clear, if on the same plane, in the sense, if you go to the basics, three-dimensional Cartesian coordinate system, we have three planes, right? XY plane, then YZ plane and XZ plane. So, if both electric field and magnetic field is lying on same plane, in the sense either in XY plane or XZ plane or YZ plane, this is the first condition. This electric field and magnetic field should be lying in the same plane. It is lying in the same plane, as well as these fields, as we have seen in the previous video, is responsible for that variation, del square E or del square H variation, creating a traveling wave. Then such a wave can be called as plane wave. To be more clear, the waves which whatever we have discussed in the previous video, the wave equation whatever we have discussed in the previous video doesn't have any such condition, in the sense the electric field can independently travel in XY plane and your magnetic field can independently travel in some other plane. Even then, those equations which we have derived stands good. But in practicality, most of the times, the electromagnetic waves are uniform plane waves. In the sense, electromagnetic waves, that is electric and magnetic fields, travel together in a single plane, or they exist in single plane. Okay, so I hope that is very clear. So if an electric field and magnetic field lies in the same plane and is responsible for a wave, then such waves can be called as plane waves. If so, what is this uniform plane wave? So that is plane wave. Now what is this uniform plane wave? See, already a wave is formed because the effect under the effect of this electric and magnetic field lying in the same plane, and if this wave has amplitude and phase, both phase and magnitude, constant over this entire plane, then I can say that it is uniform plane wave. Concept is same. We say uniform electric field, right? We said uniform magnetic field, right? The field, if that particular electric field or magnetic field is not varying with time and space, we say that it is constant. Same way, if this traveling wave under the effect of this electric and magnetic field existing in the same plane travels without changing its phase and magnitude throughout the plane, we can call it as uniform plane wave. Now I have an image in front of you, right? I didn't talk anything about that till now. So once you have these two clear cut ideas of plane wave in your mind, that is what is that? The first point is a plane wave is that wave where both electric and magnetic field responsible for that wave will be lying on same plane. And the second point is both these vectors, that is E vector and H vector, should have same amplitude and phase throughout the plane. Then I can call such waves as uniform plane waves. So we are not discussing in detail plane waves, we will be discussing in detail uniform plane waves. So again the reason is mathematical simplicity, because if E and H are not constant throughout the plane, the mathematical derivation becomes more complex. So we just assume that it is constant and we derive equation for uniform plane wave, and later we will realize that most of the waves agree with our assumption. Most of the waves are uniform plane waves. Yeah, again coming back to the figure, is something which is very interesting. You might have come across this, you might have studied this without knowing what it is in your earlier engineering physics classes or PU physics classes. That doesn't matter. I'll just refresh this. So this is an electromagnetic wave representation. Okay, I have drawn this entire figure on an XY plane, because this is XY plane. So this E and H variation is happening in XY plane, and this is my Z axis. Okay, you can assume that this is X and this is Y, or either way, doesn't matter for me. Okay, but you have to understand that this is Z. Okay, so for simplicity, let me assume that this is X axis and this is Y axis and this is Z axis. So you can see that this is my E varying like this. Okay, this is my E and this is my H. The shaded portion is my H. This is my H. Okay, so we usually assume a nearly sinusoidal or a sinusoidal shape for the wave, so that again that simplify my job of finding particular expression or solving particular wave mathematically. Okay, or later we will discuss that this will take a shape of sine wave or a cosine wave. Okay, so at this point of time you should not worry why the shape is sinusoidal. Okay, so as you can see here, the wave is starting from the origin, so I have to talk that this is a sinusoidal wave, right? Cosine wave is not possible. Okay, so this is my E and this is my H. But what is the point? What I am trying to say here is, you have to understand that this E and H will be always perpendicular to each other. Even though they are traveling in same plane, they will be perpendicular to each other. That is E vector, you know how to draw E vector. H vector, you know how to draw H vector. So if you try to put this on a plane of paper, this E vector and H vector will be at right angle, they will be perpendicular to each other. This was found from experiments. This is not to simplify the derivation, this is how it is. These are found from the real physical experiments. Okay, so this point you can remember. What is the point you have to remember? Even though E and H, okay, E vector and H vector is traveling in the same plane to form a wave, they are at right angles. They are not in phase. Their phases, their time period, everything remains same. Their magnitude remains same. Okay, independently. That is the meaning. Okay, so whatever you have here, this electric field in one axis and magnetic field in another axis. So this will help me to notate or to use E in one direction, that is E is going to have only X component and H is having only Y component, and the resulting wave is going to travel in the third axis, that is Z axis. So I hope this figure helps you or helped you to understand or have an idea about how a uniform plane wave will be formed and how the interdependency or how E vector and H vector are related. So for deriving uniform plane wave equation in free space, I will assume an electromagnetic wave traveling in free space. and I'll be considering electric field in x direction and magnetic field in y direction. Okay, both field vector does not vary with respect to each other. That's very important. Okay, just now I explained, but still, before we start derivation, this point has to be very clear. I'll repeat, that is, both field vectors, that is E vector and H vector, will not vary with respect to each other. That means that E vector will vary only in x direction. E vector is not going to vary in y direction. Same way, H vector is going to vary only in y direction. It does not have any component along x direction. As I told you, they are independent. They are at 90 degree. Okay, and both this Hy and Ex will vary along z direction, because that is the direction in which my wave is propagating, traveling. So both E and H will vary in time and space along z direction. Remembering the definition of wave, I told you that a wave will travel, right, or a wave will vary with time and space. So here it is going to, from this point, it is going to travel along z direction as time goes by and as the space consumed by. Okay, so that's why I told, so both Ex and Hy will vary along z, which gives me space variation, and you have to remember that both field will change with respect to time also. Okay, so this is all illustrated in this figure, in this simple figure. Okay, so I'll start deriving this with respect to Maxwell's equation from Ampere circuital law. So we know that curl of H is sigma E plus del bar d by del bar t, or del bar epsilon E by del bar t, whatever. But here it's clearly mentioned that I am going to derive this uniform plane wave equation in free space. So in free space, when I say free space, it is charge free space. So there is no question of conductivity here. Okay, so this term is going to be 0. So this equation, Maxwell's equation, will be slightly modified for our purpose as curl of H equals del bar d by del bar. And mathematically we know that we express curl of H in determinant form, right, for solving it mathematically. So when I represent this in determinant form, I have these three terms with respect to Hx, Hy and Hz, right. So this is determinant of, this is how we find the determinant, if you remember. So this is equal to del bar d by del bar t. Okay, but here we know that only Hy component is present, right. I will not be going on repeating that now. By this time it should be thorough, right. Only Hy component is present. There is no question of Hz or Hx. So in this particular equation, right, there is no question of Hx and there is no question of Hz. So both these will be treated as zeros. Hope that is clear, right. Yeah, now let us find the determinant with respect to this equation. Okay, and let us expand the RHS also. So RHS says it is del bar d by del bar t, and we know that d vector can be written as dx x cap, okay, can be represented as dx x cap, dy ay cap plus dz az cap. Okay, this is well known. Okay, so finding the determinant of LHS and expanding or substituting d with respect to this, I rewrite this equation as, so finding the determinant, this 0, so minus, I have minus del bar Hy by del bar z ax cap plus this both terms will be 0, so I will have az cap term with respect to Hy So day bar hy. So finding determinant is very straightforward. Az cap. So this will be equal to day bar dx by day bar t along x direction, because I am just using this here, okay, d vector here, plus variation of y component, okay, dy component with respect to time along y direction, and then variation of z component along z direction. That's fine. Okay, now see here, what about this term, that is day bar hy by day bar x? What does this convey to you? Day bar hy by day bar x, what does it convey to you? This convey you that I am trying to find variation of hy along x direction. What is the assumption we made? H cannot have any component in direction of E vector, and E vector cannot have any component because they are mutually perpendicular. So hy cannot vary along x direction, or in other term, variation of hy along x direction is going to be 0. This is 0. Okay, so my LHS reduces to minus day bar. So this is purely conceptual. Okay, that is 0 from the concept what we have started with. So day bar minus day bar hy day bar z x cap will be equal to this entire right hand term, day bar dx by day bar t x cap plus day bar dy by day bar t ay cap plus day bar dz by day bar t az cap. Now on left hand side I have only x cap term, and right hand side I have all terms in all the 3 dimensions. Okay, so now I will be interesting in comparing the coefficients. So when I compare the coefficients, means because it's basically LHS equal to RHS equation, so if I compare the coefficients, I get for ax cap I have day bar dx by day bar t equal to this, and for ay cap there is no terms here, that means day bar dy by day bar t is 0, and day bar dz by day bar t is also 0. Okay, this makes sense because dy is can be treated as ey and dz can be treated as ez. So we have already told that E is not varying in x direction or z direction. So with respect to time, with respect to space, as well as with respect to time, that has to be 0. So that way also you can look into it, but it's very easy. It is better to compare the coefficients. Okay, mathematically we say that we are comparing the coefficients, or we can put the concept here and this 2 will be anyway 0, so this will be equal to this anyway. Okay, so basically while comparing the coefficients, existing coefficients, I can say that minus day bar hy by day bar z is equal to day bar dx by day bar, right? So if I consider dx as epsilon ex, this equation can be further written in the form day bar hy by day bar z is equal to minus epsilon. So I just take this dx as epsilon ex and negative sign to the RHS. So I get day bar hy day bar z equal to minus epsilon day bar ex by day bar t. So let me write it as first equation for later reference. Now we will be continuing with by using Maxwell's equation from Faraday's law. Okay, so Maxwell's equation in Faraday's law, this particular equation we needed for later reference. Okay, so now from Maxwell's equation from Faraday's law we have curl of E. Okay, curl of E equals minus day bar B by day bar t. So again here curl of E can be mathematically evaluated in determinant form. So writing it in that form, Ax cap, Ay cap, Az cap, partial differential with respect to x, partial differential with respect to y, partial difference with respect to z, and Ex, Ey, Ez. So determinant of this is equal to minus d bar b by d bar t. And as you know, here we don't have Ey component as well as Ez component. We just have Ex component. So these two components will be 0, and b vector will be written in the form of bx x cap plus by ay cap plus bz az cap. So considering these two, changes, let me write the determinant. So determinant, if I calculate, I'll find it as d bar Ex by d bar z ay cap minus partial differential of Ex with respect to y az cap. Remaining terms will be 0. So this will be equal to minus of, okay, I'll take minus of partial differential of bx with respect to time in x direction, variation of by with respect to time in y direction, and variation of bz with respect to time in z direction. Okay, now what we know, we already know that Ex cannot vary in y direction, right? Because in y direction we have h there. So h and E cannot be in same direction as we were discussing at the beginning point of this derivation. So this has to be 0. So we have d bar Ex by d bar z ay cap is equal to this entire term on the right hand side. Again, going with the same way of mathematical solution, that is comparing the coefficients of LHS and RHS. So I have to just consider the ay cap. Don't forget this negative sign. So negative d bar by d bar t ay cap will be equal to d bar Ex by d bar z ay cap. So I write it as d bar Ex by d bar z ay cap is equal to minus d bar by d bar t ay cap. So I just have to cancel out this ay cap term. So I get this equation. So I get d bar Ex by d bar z as this. Okay. Now writing it in better form, that is by substituting what is by, this can be written as minus mu d bar Hy by d bar t. So for my later reference, let me take it as equation number 2. Okay, so we have now two equations, equation number 2 and equation number 1. So what we have, the equation number 1 was d bar Hy by d bar z, that is variation of Hy in z direction. That is first equation. And here we have variation of Ex in z direction. So if you refer the figure, what does it mean? Now see, it's interesting. It directly gives you, see, the variation of Hy, how Hy is traveling in z direction and how Ex is traveling in z direction, right? So equation number 1 is giving me how Hy is traveling in z direction. So the variation of d bar Hy by d bar z means the variation of Hy in z direction. So variation of Hy in z direction will be given by this particular mathematical expression. Same way, I also have how Ex is varying in z direction. So this particular expression will give me that variation in z direction. Okay, so you have these two equations independently expressing how Ex and Hy travel in z direction. But that is not enough for us. We should be able to find out how an electromagnetic wave travel. That is how, what is the joint effect of Ex and Hy in Z direction. Agree? So somehow we need to relate equation number 1 and 2. For that, what I do is I do some mathematical adjustments, as I call it. So we take partial derivative of equation 1 with respect to t. So let me take partial differential of equation 1, okay, partial differential of equation 1 with respect to t, time. So if I partially differentiate equation 1 with respect to time, I have to partially differentiate the variation of Hy along z direction with respect to time, right? So this will be equal to minus epsilon. So I have del bar by del bar t on RHS. So now it becomes del bar square by del bar t square Ex. Okay, please verify with equation number 1. I have just substituted or partially differentiated the equation number 1 with respect to t, that's it. Okay, so this will be kept for my later reference. I also do one more thing. I just take partial derivative of equation number 2 with respect to z. Okay, so I'm going to take partial differential of equation 2 with respect to z. Now why I am concentrating, so it's a mathematical way of viewing it. Okay, I have two independent equation number 1 and equation number 2. Both give me variation of Ex and Hy in direction of z. I agree, but I need to have some interdependency of these two variations, because both are in same plane and both are having constant amplitude and phase and both are traveling in same direction, that is it. So it's always better to have a single equation, an interdependent equation, which gives me the idea of variation of Ex and Hy in z direction with respect to time. Is it not? For that, I have to relate equation number 1 and equation number 2. To do that, I am doing some mathematical adjustment. I call it as an adjustment. Okay, I repeat, I call it as an adjustment. That's it. Not the engineers or the other physical engineers. Okay, I call it as an adjustment because it's necessary for you to remember what I am doing on equation number 1, what I am operating on equation number 1 and what I am operating on my reference equation number 2. For equation number 1, I am going to differentiate it, I am going to find the variation with respect to time again, and for the second equation I am trying to find the variation with respect to z. Now why particularly t and why particularly z? By this point of time it should be clear for you. Why? Because the wave varies with space and time. So with respect to z, if I do, I will get the variation with respect to space. With respect to t, if I do, with respect to time, I will get the variation with respect to time. So I need both time and space. And it is z because you know that the wave is traveling in z direction. That's why I did not take x or y. I am particular in taking z. Is that clear? But you should understand that I am applying with respect to t on equation number 1 and with respect to z on equation number 2. This you have to follow, otherwise you are going to get stuck somewhere here in the derivation. That's why I call it as a mathematical adjustment, nothing else. For you, for making you to remember which, with respect to which I have to derive which equation. Okay, now partially differentiating equation number 2 with respect to z, that is this equation. Okay, equation number 2 with respect to z, what I get? Yeah, I will get double differential of Ex, which is equal to minus mu del bar by del bar z of del bar Hy by del bar t. Okay, I am partially differentiating equation number 2 again. So I will just rearrange the things. Okay, I will keep this del bar by del bar z, del bar h by del bar t here. This mu I will take it to other side. Okay, so doing some manipulations there, I can write this equation as del bar by del bar z of all these manipulations are done so that I get a direct relation between equation number 1 and 2. Okay, so del bar Hy by deba t will be equal to, this mu goes the other side, so this becomes 1 by mu, so minus 1 by mu deba square Ex by deba z square. Okay, now I can interchange this operand, doesn't matter, it can be partial differential of this term, in the sense I will find partial differential of hy with respect to time, then find partial differential with respect to space, or the other way around, both will give me same mathematical result. In the sense I can find deba hy by deba z first, then deba by deba t, or the other way, doesn't matter. So I am just interchanging this operands to get some better relation. So I just interchange this operands of LHS. So deba by deba t of deba hy by deba z, mathematically it is not going to affect me, so I can do that. So this gives me minus 1 by mu deba square Ex by deba z square. So this I will keep it as equation number 4 for reference, present reference. Now see, can you compare now equation number 3 and 4? So to get a relation between equation number 1 and 2, I did some mathematical manipulation and I got new two equations, equation number 3 and equation number 4. Right. Now at this point of time, can you relate now equation number 3 and equation number 4? A big yes will be your answer. Is it not? It will be a big yes. Why? Because the LHS looks same. So I can equate the RHS. You can see here, this is same. The LHS is same. So I can easily equate RHS. So when I equate RHS, what I get? Minus epsilon deba square Ex by deba t square is equal to minus 1 by mu deba square Ex by deba z square. So let me rearrange these terms. I will try to bring these constant terms epsilon and mu onto the same side. Okay, and on both sides I have negative, so I can neglect it. So this equation can be written something like this: deba square Ex by deba z square is equal to, okay, just rearranging, doesn't matter which is LHS RHS, okay, you should not confuse with that, just, or you can keep it in RHS itself, but I just want this mu to come on the other side. Okay, so mu epsilon deba square Ex by deba t square, or I can write this as deba square Ex by deba z square minus mu epsilon deba square Ex by deba t square equal to 0. I taken this the other side, so equal to 0. Okay, interestingly we arrived at uniform plane wave equation in free space. Now look at this equation, what you can infer from this equation. So now I have a very good equation, okay, which we have explained theoretically, conceptually at the beginning of this derivation. See here, I have variation of Ex. Remembering the general wave equation, was del square E, del square H, del square D, del square B. It is del square. Del square is nothing but partial differential square. So here also in LHS or in this particular equation, I have del square. Okay, so see here, it is del square by del z square. Okay, so del square variation of Ex in space, because my wave is traveling in z direction. So double variation along space minus medium constant values, because the traveling wave always depends upon the medium, right? Wave will not travel same as in air, in water, or in glass, or in any other copper wire medium, conductor, whatever. Okay, so it depends upon the medium also. So this is the effect, that medium effect will be taken care by this term. So minus mu epsilon and variation of Ex with respect to time. Getting? So here is double variation with respect to space, here I have double variation with respect to time, okay, with respect to the medium. So this is my uniform plane wave equation in free space. Now at this moment you will be wondering, in the general wave equation I have written equation in terms of E, I have written in terms of H, I have written in terms of all that. But here I am getting an equation in terms of electric field only. But this is interesting. There you see, you got the same equation. What you did, you just replaced, right? In the previous video I am talking about. There you just replace this E by H, you got another equation. Same way here also, this is the general uniform plane wave equation which tells you the behavior. I hope this equation is clear, right? Double variation of Ex with respect to space, that is along z direction. Double variation of Ex with respect to time. Okay, and these terms mu epsilon is taking care of effect of the medium. Okay, keeping this in mind, from the general wave equation we know that if I replace this Ex by Hy here and here, I am going to get the uniform plane wave equation with respect to magnetic field. It doesn't create any difference. Okay, or in other words, if you could calculate the behavior, or if you could analyze the behavior of an uniform plane wave with respect to this equation, it is true for the effect of magnetic field also, because it is going to have same phase, it is going to have same magnitude. Only difference is E and H are mutually perpendicular to each other. Is that fine? So I can easily say this is uniform plane wave equation in free space. Okay, so this is nothing but uniform plane wave, UPW we call UPW equation, uniform plane wave equation. Nice. Now if you want to, and one more thing we can infer from here is, even though already discussed, you have to understand that this wave is traveling in some shape in Z direction. Okay, that's why we have here deba z square. It is not necessary that this wave should always travel in Z direction. You should not have that hypothesis in your mind, because I considered E in X direction, H in Y direction, that's why the wave was traveling in Z. If I consider some other plane, that is E is in Z direction and H is in Y direction, then the wave will be traveling in X direction. Then this equation will have deba square, okay, Ey by deba x square. So that has to be very clear in your mind. Okay, this is just a general equation for uniform plane wave. Okay, that said, now my duty, or now at this point of time I am interested in finding what is the velocity of this wave. Is it not? It is nice to find. I understood that the electric field and magnetic field are interdependent. Okay, they form together a wave, and that wave can travel. That wave can carry energy. That wave can transfer energy, transfer information. We have seen this with examples in the previous videos, right? Ripples of water may be, sea wave may be, right? Audibility may be, right? All these carries energy or information. Now, at this point of time, it is necessary to know at what speed it carries the information. What is the velocity of this wave which is traveling in Z direction? Is it not interesting to find out? Yes, I believe. So for that, I'll be comparing this uniform plane wave. Okay, I'll be comparing this uniform plane wave equation with an existing classical wave equation. Okay, so I have a classical wave equation, okay, given by del square F, where F indicates general field. Okay, so del square F by minus 1 by V square deba square F by deba T square equal to 0. This is known as classical wave equation. This is nothing to do with our electric field or magnetic field, or nothing to do with our electromagnetic wave. Okay, so this is known as classical wave equation, which is already derived. We are not going to derive it and waste our time. Okay, so you have to just remember that this is classical wave equation for any field f. So del square f minus 1 by v square del square f, where v is the velocity of the wave. Now if I compare this equation with my existing equation, what is my existing equation? My existing equation is del bar square ex by del bar z square minus medium terms, that is minus mu epsilon del bar square ex by del bar t square equal to 0. So you are asked to compare these two equations. So here del square is nothing but del bar square by del bar z square or x square or y square, whatever. So del bar square by del bar term square is del square, and here also I have del bar square by del bar t square. So this f vector can be treated as ex equivalent to ex. So when you compare these two equations, what catches my attention is 1 by v square can be directly compared with mu epsilon, right? In this particular equation, this term 1 by v square term is mu epsilon here. So when I compare, I can say that 1 by v square in this classical wave equation is nothing but mu epsilon in my UPW equation, uniform plane wave equation. Right? So what does this tells me? If 1 by v square is mu epsilon, it directly tells me that v is 1 by mu, or I will write it this way, v square is 1 by mu epsilon, right? Or this directly tells me that v is, or velocity, v is 1 by square root of mu epsilon. This is very important result. See, now I have the velocity. The velocity of uniform plane wave is 1 by square root of mu epsilon. And we are deriving this uniform plane wave in free space. Should not forget that. In free space, in charge free area or charge free space. So in free space, we know that mu is mu naught and epsilon is epsilon naught, because mu r will be 1. This is because mu r and epsilon r both are 1 in free space. So this is nothing but 1 by square root of mu naught epsilon naught. And what is more surprising, mu naught and epsilon naught values we are thorough with. We know, right? Mu naught and epsilon naught values we know already. What is mu naught value and what is epsilon naught value? Mu naught is 4 pi into 10 power minus 7. Epsilon naught is 8.85 into 10 power minus 12. We know that. Okay, it's not a question mark, we know that. So we can substitute that here, and if we substitute and calculate, we will find that velocity will be 3 into 10 power minus 8 meter per second. Just substitute this, okay, don't approximate much. Just substitute the value of mu naught epsilon naught and find it in your calculator. You will find that v will be 3 into 10 power minus 8 meter per second. And have we come across this number somewhere before? 3 into 10 power minus 8 meter per second. Exactly, this is the velocity of light in free space, right? Is it not? This is the velocity of light in free space. There are many discussions carrying out. There are other particles which can travel faster than light. Forget about it. We know that at this point of time, light is the fastest traveling. Okay, other discussions are going on. I agree. Yeah, I agree. But it travels at a speed of 3 into 10 power minus 8 meter per second. What this tells you? It tells you that uniform plane wave can travel at speed of light in free space. Excellent. Okay, so I have found velocity. I understood that there is an electromagnetic wave created by electric field and magnetic field. Basically, there is an electromagnetic wave forming an uniform plane wave, right? Because they are traveling in same plane and they are traveling in a particular direction with respect to the variation given by those wave equations which we have derived. All that is fine, but as a student, okay, or as an eager engineer, I was trying to find out what speed this wave is traveling. I made use of classical wave equation. I just did a comparison, and eureka, I found that the velocity of uniform plane wave is same as velocity of Light, speed of light. So keep this in your mind. The velocity of light in free space and velocity of uniform plane wave in free space is same. It's that fast. So the waves can travel speed of light. Now connect it with the previous video where I told you that light is wave. This is obvious. This is interesting. If you are interested, this is obvious. What is obvious? I told you that the visibility is due to light wave. When I say light wave, light has to travel at the speed of light itself. So if I want to call it as a light wave, the speed of the wave should be same as speed of the light. So light wave is an uniform plane wave traveling at its speed, that is 3 into 10 power minus 8 meter per second. I hope that was an interesting discussion. Thank you for watching.